Good morning, one and all present in this international conference on science and technology in Paris, France. I myself, Dr. Manoj Sahni, a faculty in the Department of Mathematics at Pandit Deendayal Petroleum University, Gujarat, India. First of all, I would like to welcome you all and thank the organizer for giving me the opportunity to interact with you all. Functionally gated materials is a very important topic, and I will show you the applications of it at each and every field which you can think of. Now, my keynote talk will be divided into the following sections. First of all, I will show you the material hierarchy, then the historical background of the functionally gated materials, its development, then followed by the advantages of the functionally gated materials and its application areas. Then we will going to discuss one mathematical model, followed by the conclusion, and the last, the references. So as I said, the representation of the modern material hierarchy, as you can see, it is starting from the lower to the upper. As you can see at the lower, you can see the base materials. These base materials are being taken from the periodic table, which is being classified into organic and inorganic, which is again being classified into the elastomer, polymer, glasses, metals, and ceramic. Now, if you move ahead, it will club into the composite materials. Composite material is a material which is being made from more than one material. And the last at the top, it is a functionally gated materials, which we also call it as a innovative composite materials. So the common question that comes into the mind is, what is the need of the functionally gated materials if you have a composite materials? There is a drawback in the composite materials, that composite materials fails under various severe conditions which the FGM can sustain. So advanced materials which can sustain the fatigue, as well as the stresses can be equally distributed. This functionally gated materials can too, which is also act as a non-homogeneous materials. That we're going to see it in the slides ahead. So why do we study the material science, and why do we require the knowledge of the material science and engineering? Firstly, to select a material for a given use based on the consideration of the cost and the performance. Secondly, to understand the limits of the materials and the change of their properties with their uses. Thirdly, to be able to create a new material that will have some desirable properties, because every industry uses different materials and their requirements are different. So you require the functionally gated materials differently for different industries. Now, the historical perspective is the origin of the human life always are related with the materials. With the development of the human life, which we call it as the Stone Age, people used natural materials like stone, clay, wood, and many more. With the ahead of the Stone Age, which we call it as a Bronze Age in 3000 BC, with the development of the copper, and the major development that took place in 1850 with the discovery of a steel, which is actually being the pillar of the development of the modern era, because steel is being used in everywhere, and as an example, it is being used in the modern infrastructure of the industrial world. Now, classification of the materials. Materials are being classified according to the structural properties or their uses. Like metals, as an example, you have an aluminum, steel, brass, and gold. As a semiconductors, which are good have an electrical properties and depend strongly on the minute properties of the containments, like silicon and germanium. And ceramics, they are usually combinations of metals or semiconductors. And example like porcelain, glass, these are all ceramics. Polymers, They are usually based on the H and C, hydrogen and carbon, and other non-metallic elements, and they are light in weight. As an example, there are plastics and rubber. And in the current scenario, we have a development which we call it as biomaterials. Now, these biomaterials that is being used to replace the human body parts like teeth, orthopedic, knee surgery that is being done using the biomaterials, and many more of them are there. Now, as I said, composite materials, which is being developed as a space-age materials, but now they are no longer being called as a space-age materials with the development in the 1980s of the functionally gated materials. But still, the composites are being used at various places like sporting and recreational accessories, in aircraft and military, and in the automobile sector, transportation, civil infrastructure sector like buildings, roads, and bridges, in the constructions like swimming pools, bathroom fixtures, wall panels, and like corrosion resistant equipment. It is also being used as a corrosion resistant equipment. It is also being used as an electrical and electronic applications like line hardware, substation equipment, microwave antennas, and many more. In a marine, it can be used as a naval boats and ships. Now, if the composites are being used at various places, so what is the need arises for the advanced materials? Now, composite materials will fail under extreme working conditions through a process called delamination. Now, what is delamination? Delamination is the separation of fibers from the matrix. So materials used in advanced application usually designed for maximum performance and normally expensive. So like titanium alloys for supersonic airplanes, magnetic alloys for computer disks, ceramics for the heat shield of the space shuttles, and there are many more that is being used. Now, what is delamination? As you can see in the figure, that there is an overlapping of the fibers. Now, because of that, the structure fails and the fatigue occurs. Now, it is because the stress concentration at a particular point is more. So stress should be equally distributed, and it should be continuously distributed so that it should not concentrate at one point. Now, this delamination is being removed by the development of the functionally gated materials. So this functionally gated materials is actually being developed by the Japanese scientists in 1980s. And that is being developed when they have faced a challenge in a hypersonic space plane project, which requires a thermal barrier with an outside temperature of 2000 Kelvin and inside temperature of 1000 Kelvin across a very less 10 mm thickness. So they came up with a new material which they coined it as a functionally gated materials. Now, as I said, FGM is also called as an innovative composite materials. FGM are entirely different from the conventional alloys or composites in which the mechanical, electrical, magnetic properties, they vary smoothly from one interfacial layer to another interfacial layer. So they are non-homogeneous materials, whereas composite materials are homogeneous materials. So they are equally being used from across the layer, which FGM, there is a variation continuously from one interfacial layer to another interfacial layer. So they do not allow the stress concentration at a particular point. Now, as you see in this diagram, here E is actually representing the Young's modulus, alpha is representing the coefficient of thermal expansion, and nu is representing the Poisson ratio. So that is being varying continuously from one layer to another layer. And when they are varying from one layer to another layer, so in that case, they are continuously, that is, there is a matching at one layer when you move from E1 to E2. So at a particular layer, that E1 and E2 is matching. So there is a movement, continuous movement, and there is no break. As you can see it here, that is traditional composite materials, there is a straight line that are homogeneously distributed from across one section to another section, whereas functionally graded materials, as you can see it in the diagram, it is continuously moving from one interfacial layer to another interfacial layer. So it actually saves the cost also, but the fabrication process cost is actually high. So it is difficult to manufacture as compared to the traditional composite materials. So what is the importance of the functionally gated materials? Functionally gated materials eliminates the sharp interfaces existing between the composite materials, from the composite materials, which is where the failure is initiated. It replaces this sharp interface with a gradient surface, which produces smooth transition from one material to the next layer. And thirdly, the toughness of a metal can be mated with the refractiveness of the ceramic without any compromise in the toughness of the metal side or the refractiveness of the ceramic side. So if you require the metal more on the one side and less on the other side, and whereas ceramic less on the one side and ceramic higher on the other side, then you can accordingly mate both this metal ceramic as per the requirement of the materials. So what is the advantage of the functionally gated materials? We have seen it. So it is a better adherence of a protective layer. Secondly, minimization of interfacial stresses between different materials, that is evenly distributed. Thirdly, increase in the local fracture toughness, that is because of the local fracture toughness, the strength of the material increases. Fourthly, the relocation of maximum stresses on a load bearing component. So the classification of the functionally graded materials, it can be like this. It can be the metal, it can be mated, ceramic metal, ceramic, metal with polymer alloys, and all others it can be done according to the requirement of the industry. So there are various applications of the functionally graded materials. It is being used in the aerospace industry now, in the nuclear energy, as a biomaterials, energy conservations, electronics and optoelectronics, in the chemical plant, in the medical side. There are many applications of the functionally gated materials that we will see in it. In the aerospace and aeronautics industry, this FGM are particularly used as a thermal barriers in space vehicles. In the defense industry, it is being used as a penetration resistant materials, which is being used for the development of the armor plates and bulletproof jackets. In the medical side, it is being used in the teeth and bone replacement. In the thermal barrier coatings, it is acting as a thermal barrier coatings, which are highly advanced material system usually applied to metallic surface such as gas turbine or aero engine parts. In others, manufacturing tools like machine tools, it is being used, forming and cutting tools, metal casting and forging process. In the electronics and optoelectronics, it is being used in the optical fibers, computer circuit boards, and cellular phones. So, for the modeling of any functionally gated materials, if we are studying the behavior of the mechanical properties or the electrical properties or the magnetic properties, we require the variation of their properties, and there should be a preset, that it can be a linear variation, it can be a non-linear variation like exponential, reciprocal, or any polynomial one. So this should be preset before you are going into the modeling of it. So I've taken one example to explain the mathematical model of a functionally gated materials. So I've taken a thick walled circular disc. As you can see, it's an annular disc, thick walled, with an internal and external radii A and B, and it is being subjected to an external pressure with the boundary conditions. As you can see it here, TRR is equal to 0 at R equal to A, and TRR is equal to minus P. Now minus P is because the pressure is acting from outside inside. So that is why minus sign is representing the negative direction, that is, it is acting inside, as well as TRR is representing the radial stress which is acting outside. So they are both opposite in direction. Okay, so this is also moving with an angular velocity omega. So as I said before, there should be a preset variation of the property. So I have taken the variation of the property as Young's modulus in the form as E naught R by B raised to the power n. Now this is a power law, and similarly I have taken the variation of the thickness from inside to outside in the power law itself. Now for the study we require some functionally graded materials. So I have taken an aluminum alloy 7075P6. Now what is the advantage of this aluminum alloy? That we will be seeing it. It is very strong, equivalent to the strength of the steels. Okay, and 7075P6 are often used in transport applications including marine, automotive and aviation. So it has a very high strength to density ratio, and this is a aluminum alloy which is being used at various places. So that is why I have done the analysis of an aluminum alloy. Now, to study any mathematical model, we require three mechanical equations. First, the equation of equilibrium, that is represented by equation number 1. Second, the strain compatibility equation, equation number 4. And the next, that is equation number 5, that is stress strain relationship. Now I have used a method that is, we call it as stress function method. I will be choosing a function in such a way so that the equation of equilibrium is satisfied. So I have substituted equation number 5 and 6. Equation number 5 and 6, I am substituting it in equation number 4 and using the equation number 2, that is preset variation. And simplifying it, I will be getting this second order ordinary differential equation, which we call it as Cauchy-Euler differential equation. This Cauchy-Euler differential equation is actually being solved using, which we call it as a complementary function and a particular integral. So we find out the CF, which is for the homogeneous differential equation, and particular integral for the non-homogeneous differential equation. So we have found this first two terms is representing of TRR as the complementary function, and the third term is representing the particular integral, where A is being calculated, that is at the down. Now A1 and A2 are arbitrary constant, so we require the two conditions for it. So we have the boundary conditions, that is internal pressure is 0 and external pressure is minus P. So using that, we have calculated A1 and A2, and this A1 and A2 will going to substitute it in TRR and T theta theta, and we'll be able to find out the radial and circumferential stresses at each radii points between A and B. Now if we are able to find out TR and T theta theta, we are also able to find out the strains in equation number 5. Because we know ER, we are able to find out TR and T theta, Poisson ratio is constant, so we are able to calculate the radial and circumferential strain. Okay, and if we are able to find out the circumferential and radial strain, so using equation number 3, we are able to find out the displacement at each radial point. So this is the values that we have taken it for the aluminum alloy, that is internal external radii is 50 and 100 mm with an angular velocity of 250 radian per second, that is the disk is rotating, with E naught as 72,000 MPa, and the material index, that is n equal to 0, is representing for homogeneous, and 0.3 and 0.3 is for a non-linear variation. Now we have an external pressure, P is equal to 0 representing there is no external pressure, and P is equal to 20 representing there is an external pressure, and H naught value is being taken as 2.4. So the figure shows the variation of the Young's modulus and thickness from internal to external radii, that is 0.5 to 1. As you can see with a straight line, that straight line representing it is a homogeneous variation, and which is not a straight line is representing the non-linear variation. So the radial stress, if you see the figure number 2a, that is, if there is no pressure, then the radial stress at the boundaries are 0, and the peak occurs near about at the middle point, that is 0.7. Whereas if we apply the pressure from the outside, external pressure is being applied, then there is a shift at the peak from 0.7 to near about 0.625. Now, because of the external pressure, it forces the radial stress peak at the internal. And in the figure 3, the circumferential stress is being drawn. And if you see it here, when you apply the pressure at the end, external pressure is being applied, as in figure 3b, the circumferential stress is less as when the pressure is not applied. So circumferential stress always act as a resisting stress, whereas radial stress may try to push the points outside, and the circumferential stress always tries to resist that. So that is why, as you can see, the circumferential stress is always more than the radial stress, as you can see it here, both sides. So similarly, you can draw the graphs of the strains. As I told you, you can find the strains at each radial points as well as the displacement. So my conclusion of the talk is FGMs are now recognized as important composite materials throughout the world. Secondly, utilization of the functionally gated materials appears to be one of the most efficient and effective materials in achieving sustainable development in industries, as this is very, very important that is being used in industries. Thirdly, FGM are constructed to use most of the material properties in the best possible way. Fourth, there's a wide range of applications of FGM, and it is expected to increase as the cost of material processing and fabrication processes are reduced by improving these processes. So many other researchers agreed and reported that functionally gated materials could provide the implant a suitable stiffness to endure the physiological loading, and that the graded porosity structure could enhance the mechanical, electrical, magnetic property of the implant to optimize the material's response to external loading. Last, the functionally gated material is an excellent advanced material that will going to revolutionize the manufacturing industry in the 21st century. Now, these are the books on the functionally gated materials. If somebody wants to read more on the functionally gated materials, innovative class materials, they can refer these books. Last, the references. I have taken some of the portions from these references. These are some more references, some more, and some more. And the last, this one, these two, 22nd and 23rd. These are my two research papers that has been published recently. You can refer my papers also. And if you want any guidance or you want to collaborate with me, you can write to my email ID that is being listed here, manojsahni117@gmail.com, and you can see it here also. You can see it here, my email ID, manojsahni117@gmail.com. You can, if anybody wants to collaborate, he or she is most welcome. And I would like to thank the organizer again for giving me an opportunity to interact with you all. You're all very good audience, and I enjoyed this session a lot with you. And thank you so much for listening me. for the last 20-25 minutes. Thank you once again